In this video, we are going to look at vertex coloring. A coloring or a vertex coloring of a graph is one in which no two adjacent vertices are the same color. So one way we could color the vertices of this graph, for example, is to color every vertex a different color. And that would certainly be one vertex coloring, but it's not one that's very interesting or special in any way. The more interesting problem is to color a graph using the fewest number of colors necessary. So, for example, if I would start by coloring the same vertex red as I did in the previous graph in the upper left corner, then what I would do is I would move on to another vertex. So I'm going to move over to the right. Because this vertex to the right is adjacent to my red vertex, I would have to color this with a different color. So I'll color it blue. Then moving on to the next vertex, let's look at this one right here. The goal would be to color it using an existing color. In other words, using red or blue if I could. But notice that this is adjacent to the red vertex, and it's also adjacent to the blue vertex, which means I'm going to need a different color. So I'll color it green. Moving across to the next vertex, again, the goal would be to not have to grab a new color. So the goal would be to use red, blue, or green. So looking at this vertex, I cannot color it red because it's adjacent to red, but I could choose to color it either blue or green. I'll choose blue. And then last but not least, when we come down to this vertex, again, the goal would be to not pick up a new color if I don't have to. And so I notice that this vertex is adjacent to green and blue, but it is not adjacent to a red vertex. And so the fewest number of colors needed to color the graph would be 3 colors. So the number of colors, the fewest number of colors required to color a graph is known as the chromatic number. So let's find the chromatic number of these graphs. So for the first one, I'm going to color vertex number 1 red. Then I'm going to go over to vertex number 2, and I can't color it red because again, 1 and 2 are adjacent. So I'm going to color this vertex blue. When I go to vertex 3, notice I can't color it blue because I'm adjacent to blue, but I can color it red. And again, the goal would be to not introduce another color unless I have to. Going on to vertex 4 is adjacent to 1, which has been colored red. So that means I could color it blue. Vertex number 5 is adjacent to the number 2 and number 4, which are both colored blue. So I can't color it blue, but I could again use red. And then notice that vertex number 6 is adjacent to 1 and 5, which are both red. So I could color it blue. That means the chromatic number of this graph is 2 because I can color it using 2 colors. Moving on to the next graph, I can again color vertex A red. Vertex B cannot be red because it's adjacent to A, so I could color it blue. Moving over to vertex C, it is adjacent to B, which is blue, so I could color this one red. Going down to D, notice that D is adjacent to both A and B, which are red and blue, so I will have to introduce a new color. I'll use green. Moving over to E, E is adjacent to B and D, which are blue and green, so I'll use red, again, trying not to introduce a new color whenever possible. Looking at vertex F, it is only adjacent to the green vertex, so I could color it red or blue. Again, it doesn't necessarily matter. I'll pick blue, just because I'd like a little bit more blue in my drawing. Whenever I get over to vertex G, Notice G is adjacent to E and C, which are both red, and F, which is blue. So I can color it green and I won't have any issues there. And then moving over to H, as long as it's not green, I can color H either red or blue. So the chromatic number of this graph is 3. One thing you might notice is that the coloring is not unique, but the fewest number of colors needed will always be the same. For example, you could have colored graph or vertex H either red or blue, but notice that would not have changed the fewest number of colors required to color a graph, or that chromatic number, which is 3. Okay, so we can use graph colorings to solve problems about scheduling. So what I have here is a list of people who are graduating. And so each of these people, Alex, Bryson, Chloe, Dante, Evan, Fran, Ginny, and Umberto, are going to have a graduation party. And the people listed next to their names are the people that they're going to invite to their party. And what they want to do is they don't want to cause any of the friends that they have in common to have to choose between one party or another. They'd like to schedule their parties all on different days so that there is no conflict. So how can we use graph coloring to solve this? Well, one way we can do this is we can let a vertex represent each of the people graduating. So that would be Alex, here's Bryson, Chloe, Dante, Evan, Fran, Ginny, and Umberto. Okay, so each vertex represents a person. And then we can connect two vertices with an edge when they have a guest in common. So for example, Matt is being invited to Alex's party, and Matt is also being invited to Chloe's party. So we can connect Alex and Chloe together by an edge because they have a guest in common. If I continue to look for other people who are inviting Matt to their party, notice that Matt is also in common with Evan. And so I can connect Alex with Evan, A with E. And then I'm going to move on to people who are inviting Abby to their party. So still sticking with Alex, but who would invite Abby? So Abby, is in common with Chloe. So Alex and Chloe, notice I already have them connected with an edge. Abby is also in common with Fran. So Alex and Fran share someone on their guest list that's in common. We'll connect those. And that is it for Abby. She's not invited to Ginny or Umberto's party. Moving on to our next guest, Shanice. Notice that Shanice is also being invited to Ginny and Umberto's party, as well as Alex. So we're going to connect Alex to Ginny and Umberto. And then last but not least, we've got Marcus. And Marcus is being invited not only to Alex's party, but to Fran. Notice we already have an edge from Alex to Fran, A to F. And that would be it. So there are all of the people that Alex has someone on his guest list in common with other people. Now, I'm going to encourage you to continue to draw this graph. I'm going to briefly pause the video, finish the graph, and then we'll pick it back up together in just a moment. Okay, welcome back. So this should be what your graph looks like, with all of the edges, again, representing people holding a graduation party, and they are inviting the same people. So this looks like a bit of a mess, but graph coloring, vertex coloring, will actually help us solve this problem. So we're going to start, I'm going to color vertex A blue, okay? And then I want to make sure that any vertex adjacent to A, adjacent to Alex, that would mean they share a guest, we want those people to have a different party date. Okay, so I'm going to go ahead and move to C, over to Chloe. So Chloe and Alex have someone in common. That means we want their parties scheduled on different days. So I'm going to put Chloe as a green. Okay. Then looking also who A is attached to. A is attached to E. They share a guest in common. But E also shares with C. So looking at E, A is blue, C is green. I need a new color to go here. So I'm going to go ahead and use yellow for vertex E. Then when I get over to vertex F, notice that F is adjacent to A, which is blue, C, which is green, and E, which is yellow. So I can't use any of those colors again. I'm going to need a new color. I'm going to go ahead and use red. Now, when I go over to vertex G, I do notice that G is adjacent to A, so it can't be blue. But right away, I notice that G and F are not adjacent to each other. And so I notice that I can go ahead and color G red, not introducing a new color into the mix. Looking at vertex H, again, vertex H is adjacent to a red, to a blue, to a green, and to a yellow. And so I am going to have to pick up a new color for vertex H. I'm going to go ahead and color that vertex in black. Going over to vertex B, I notice that it is connected to a black and some reds, but it is not connected to my vertex that is blue. It's also not connected to a vertex that is green or yellow. And so again, I can pick any of those colors, quite honestly, but I'm going to go ahead and pick blue. And then looking at D for the last one. So again, the goal would be to not have to bring in a new color. So looking at vertex D, I notice it is adjacent to a blue, to a black, and to a couple of reds. And so as long as I don't color it blue, black, or red, I can use green or yellow. Again, doesn't matter which one, so I'm going to go ahead and choose yellow. So then what does this tell us? Well, this tells us that A and B, Alex and Bryson, can schedule their parties at the same time because they don't have any guests in common, and so they won't have to worry about any overlap. Chloe is going to schedule her party on her very own day and time. Dante and Evan can schedule their parties at the same time because, again, they don't share any guests. Fran and Jenny can schedule their parties at the same time, and then Umberto can schedule his. So again, this isn't a unique coloring. There might be other ways to do this, but it will require a minimum of 5 different days or times, if you will, for everybody to schedule their party so no one has to choose which party they would go to over someone else's.